Welcome back to Honors Calculus. In this video, we're going to be investigating using a table of integrals in order to solve integration problems. So, without any further ado, let me get my head out of the way and let's dive in. We are looking here at trying to evaluate things that kind of look like elements of our table of integrals. So remember, we have a couple of basic rules. The power rule for integrals, the integral of x to the m dx is equal to 1 over m plus 1 times x to the m plus 1 power plus some constant of integration. And that rule will work whenever m is not 1. When m is 1, you have a divide by 0 error. We have this rule, and we have a couple of rules involving trigonometry. The integral of sine x dx is equal to the negative of cosine of x, again, plus a constant of integration. The integral of cosine is equal to sine. The integral of tangent times secant is equal to secant, and the integral of secant squared is equal to tangent. And of course, we can find rules for cotangent and cosecant as well, but nobody cares about those two functions. So the question of note today is, how do you handle something like the integral of the sine of 3x? Well, we remember from our ideas related to the chain rule of differentiation that if I wanted to take the derivative of, say, the negative cosine of 3x, I would get sine of 3x times the derivative of 3x, which is 3. So just using our substitution as it stood didn't quite work. But the easy way to get rid of a factor of 3 is to divide by 3. So we see that the integral of sine of 3x is going to be negative 1/3 of the cosine of 3x. Again, as always, plus your arbitrary constant of integration. And you can check by differentiation that yes, this will in fact work, or at least it will if my 3 in here actually looks like a 3 and I hit the right button. There we go. So having arguments in our functions makes things a little bit more challenging, but still perfectly perfectly within reach. Very similar idea we can have with radicals. If I want to integrate 1 over the square root of 5x plus 1, well, I know that 1 over the square root of 5x plus 1 is simply a negative 1/2 power. This is the same thing as the integral of 5x plus 1 to the negative 1/2. And with a negative 1/2 power, then we should be looking at something where m is negative 1/2. We'll add to that, divide by positive 1/2 raised to the positive 1/2 power. But once again, if we are trying to work through this using, if we are trying to work through this using derivatives to double check, you might think that this is going to be 1 over 1/2 times 5x plus 1 to the 1/2 power. But if you took the derivative of this, you would get the 1/2s canceling each other out. You would get 5x plus 1 to the negative 1/2, and then you would multiply by the derivative of 5x plus 1. The derivative of 5x plus 1 is 5. So our guess of 1 over 1/2 times 5x plus 1 to the 1/2 power is not quite going to cut it because we have this extra factor of 5. So to solve that, we introduce another 1/5 in our original expression. I'm going to guess that this is going to be 1/5 times 1 over 1/2 times 5x plus 1 to the 1/2 power. 1/5 times 1 over 1/2 is 1/5 times 2, which is 2/5. And once again, we can double check by differentiating. If you take the derivative of 2/5 times 5x plus 1 to the 1/2 power, you get the original integrand 5x plus 1 to the negative 1/2, which is 1 over square root of 5x plus 1. This being an indefinite integral, of course, there's always the possibility of adding a constant of integration, which may not affect anything. Then we can start getting really crazy and maybe look at something like the integral of sine x over cosine squared x. This is, as I said, a little bit crazy. As a forewarning, in the next video, we're going to be looking at a more rigorous way of finding how to perform this integral. But even with just the tools at hand, we can reason our way through it, even if it's going to be a bit of a struggle. We can look at the cosine in the denominator and latch onto that and see where we can go with it. We can look at the sine in the numerator and latch onto it and see where we can go with it. Or we can look at properties of trigonometry to see where we can go with it. And that's what I want to do in this lesson. I can split this fraction up and separately write it as sine x over cosine x and 1 over cosine x. Properties of trigonometry, the ratio and reciprocal identities. Sine divided by cosine is tangent. and 1 divided by cosine is secant. And now we have transformed this from something a little bit more complicated to something that was directly on our table of integrals. The integral of tangent times secant is secant x, plus, as always, the possibility of some arbitrary constant of integration. And because the original problem was given involving sines and cosines, it's probably not a bad idea, instead of leaving the result as secant, to rewrite secant as 1 over cosine x. And that's where I would leave the problem, but there was a problem similar to this in our textbook, and when I checked the answer in the back of the book, they went a little bit crazy with it. They realized that I can take c and turn it into a fraction, multiplying top and bottom by cosine x. And then I have common denominators, and I can add across the numerator. And write this result as 1 plus c times the cosine of x all over the cosine of x. Is that better than what we had before? Honestly, I would argue not, but seeing that that is a thing you can do is worthwhile, because these are mathematically equivalent, and recognizing that you are arguing the same answer in different forms saves a lot of arguments in mathematics discussions. Let's take a look at one more example. We have so far been using these ideas to try to evaluate indefinite integrals, but the same process can work for a definite integral. So let's take a look at the integral of the square root of 2x minus 3 from x equals 3 to x equals 5. And using these same ideas, I'm going to ignore the constants of integration for a little while and just think about what would the indefinite integral of square root of 2x plus 3 look like. Well, square root of 2x plus 3 is 2x plus 3 to the 1/2 power. Using the power rule, we can see that this looks like m is 1/2, so m plus 1 is 3/2. We should get something like 1 over 3/2 times 2x plus 3 to the 3/2 power. But if I check that by taking the derivative, 1 over 3/2 times 3/2 cancel each other out, giving me 2x plus 3 to the 1/2 power, which is almost what we have, well, which is what we have. But then you'll also be taking the derivative of that inside, which is 2. Right? So our first guess didn't quite work. We have an extra factor of 2. And that's easy enough to account for. We're going to need an extra 1/2 in our final result. So we will have 1/2 times 1 over 3/2 times 2x plus 3 to the 3/2 power. And we want to evaluate that at our limits of integration, 3 and 5. I'll clean up that fraction first. Useful trick in evaluating definite integrals, you can take constant factors outside of this evaluation bracket. So we have 1/2 times 1 over 3/2. 1 over 3/2 is 2/3. 1/2 of 2/3 is 1/3. And by pulling that 1/3 out in front, that means that it's one less thing I have to worry about when I evaluate the antiderivative at the endpoints to find the definite integral. So plugging in 5, 2 times 5 is 10. Oh boy. I've gotten this far into the problem and realized that what was 2x minus 3 in the original problem turned into 2x plus 3. Luckily, that doesn't actually change much. I can just go through in the entire problem, change all of those pluses to minuses, and everything will work out because it didn't change anything in the result. And while I'm going back, I realize I also left a dx out of that line. Not a major difference, but something to pay attention to. All right. So now we're evaluating 2x minus 3 to the 3/2 power. 2 times 5 is 10. 10 minus 3 is 7. So we're looking at 7 to the 3/2 power. And 2 times 3 is 6. 6 minus 3 is 3. So we're looking at 3 to the 3/2 power. 7 to the 3/2 power is 7 times the square root of 7. 3 to the 3/2 power is 3 times the square root of 3. And distributing that 1/3 through, cancels out by the 3 in the second term, and we have 7/3 root 7 minus the square root of 3. With that in mind, I would like you to take a look at another definite integral, this time the integral from 0 to pi over 4 of the sine writing the wrong problem down. 0 to pi over 4 of the sine of 4x dx. Take a few minutes, see what you can do with that problem, and I will see you in the next video.